Saxon Advanced Mathematics. Laura and Vivian, this is a video for you to cover the problems you asked me about in our chat today. It just so happened that Laura asked me about two problems from 35, so I'll do those first, and then I'll get to lesson 36 and do the two that Vivian asked me about. Let's dive in. 35.13. This is the one with the trapezoid. And so there's a picture, and it looks like this, kind of. And instead of giving us nice numbers, John has given us algebraic values. Okay, fine. That's all the information he's given us. He says the figure shown is a trapezoid whose area equals 100 centimeters squared. Find x. Dimensions are in centimeters. Okay, so this is, as we talked about today in our chat, this is the kind of problem where you have to go backwards. We're given the answer and we're backing up to find an x. So let's remember how you approach these area problems. We went through that whole thing of how you can calculate an equation, but let's not put ourselves through that. Instead, let's just draw a line to separate this into two triangles. We'll call this area 1 and we'll call this area 2, just so we can keep it straight. Now, notice that area 1 is kind of upside down, right? Its point is down here. So what I'm imagining is we're gonna peel up that top and we're gonna flip it so that the triangle actually goes up like this. That will make x its base. And then A2 will leave just the way it is. And that will be its base. They'll both have the height of 10. Okay, I like that. So what I'm gonna do is I'm gonna write all of that out. We know that for triangle 1, the base of x times the height of 10 divided by 2, because that's the formula, right? Base times height divided by 2. That will give us the first area. Then we're gonna add the second area. That base is 2x plus 2. We better put that in parentheses to make it a quantity. We're gonna multiply that by the height, which is also 10, and we're gonna divide it by 2 because that's the formula. When we do that and add them together, right, we'll have the area of this square and the area of that square. We add them, that should be the area of the whole trapezoid, and that should be equal to 100. Okay, so we take what we know and we think about how we would do it if we were moving forward, and we fill in the blanks as much as we can. And just to write some of that down, we would say that the area of the whole trapezoid, which I'll abbreviate with a T, would be the area of triangle 1 plus the area of triangle 2. And this would be the base of the first one times the height divided by 2. And this would be the base of the second triangle times the height divided by 2. And that would also equal the area. I'm going from the broadest to the more specific to plugging in the numbers. All right, so this was my thought process, and I'm writing that down just to make it crystal clear to you how I gathered up the numbers and organized them. All right, so now we have just some algebra to do. So I'm going around my notes there. The first thing that I would like to do is get rid of these denominators. And before I multiply by a least common multiple, which would be 2, I see, oh, I can cancel because I'm multiplying these. So I can just cancel that and make it 5. And the same thing here. Even though there's addition there, I'm multiplying here. So I can cancel there as well. All right, and we will get 100 equals 5x plus, and I'm just gonna go ahead and distribute this, 10x plus 10. Okay, we'll add some like terms. We'll subtract the 10 from both sides, and we'll get 90 equals 15x. Divide both sides by 15, and we get x equals 6, right? Every 2 15s is 30. I need 3 30s. 3 times 2 is 6. That's how my brain did that. Those cancel. This is the final answer. This is the right answer. I checked. So the trick to this was not necessarily building a complete formula, because that's what John did in the solution, is he used the overall formula for trapezoids. I just did the let's divide it into triangles and then add the 2 triangles. I think that's way easier, and it feels more pure in my brain, to be honest with you. It just feels like it's more logical. Okay, so that is the first one. I hope that helps. The second one that Laura asked about from 35 is 23. And this is the domain and range problem. Okay, so there are 2 parts to this. This is 23. There's an A and there's a B. I'm gonna leave myself a little bit of room. Now in both of these, we're asked to find the domain and the range of each function. So we're gonna use function notation. And the way it's gonna look is like this. We're gonna say the domain is equal to x is an element of the real numbers such that, and then we'll put some description down here. And then we'll say the same thing about the range, right? And in this one, it'll be y. Okay? Remember that domain always correlates with x, what we call our independent variable, and range always correlates with y, what we call the dependent variable. These guys are friends. D and x are friends, r and y are friends. And then we'll write the same thing here. This is just preparing what our answer will look like, right? So I just want to get all this craziness out of the way. And I also wanted to remind you that x correlates with domain, y correlates with range. Okay, now, here's where these problems get really, really easy and fun. We look at the first graph. And we know that, we'll tackle domain first. We know that domain is driven by the x-axis. So what we're doing is we're simply looking at the picture of this graph. Notice it's a finite graph. It doesn't go on to infinity. It's got endpoints, right? In 3 directions. So for the domain, we're looking to see what's the greatest value of x and what's the lowest value of x. And so we're looking at the x-axis, and we can look above and below, whichever is necessary. But we're just looking to see which point comes the farthest to the right on the x-axis and which point goes farthest to the left. And we can say that this point has the greatest value on the x-axis, and that is 6, and the least value is -4. So we translate that to our answer like so. The values for x are between -4 and +6. And we're including these points because our function did touch 6 and -4. We'll double check that when I put the book back. So I put the equal to component into my inequality. But that's where the x ranges. The x, and oh, that's confusing. The x includes points between +6 and -4. I don't want to say it ranges between those 2 points because then you think I'm talking about the range. Oh, it's so confusing. But I'm not. I'm talking about the domain, and it extends there. That's a better verb. The domain, the x values extend from +6 to -4. Now, when we want to find the range, we just flip our perspective, and now range we associate with the y-axis. So now we're just looking at the y-axis. What's the lowest point? Well, that's down here, right? -2. And what's the highest? 3. John very helpfully labeled just up to where our number comes in. So the range will vary between -2 and +3, and we will include those values in our inequality. So it will be -2 is less than or equal to y is less than or equal to, what did I say, 3? Make sense? And let me just check my answers here. -4 and 6, -2 and 3. Yes, these are both correct. All right, so all you do is look at the picture and say, and we'll do it again here, what's the greatest value for x and what's the least value for x? +4, -4, we include those points. So we always start with the lower one and go like this. And remember, X associates with domain, so we got that in the right place. And now we're looking for the range, so we look at the Y-axis. And again, we just look at what's the highest and the lowest. The lowest is -2, highest is +2. -2 is less than or equal to Y is less than or equal to +2. All right, and the way we wrote this takes into account the fact that we have other values in between those numbers, right? This one goes all along. In this one, they both do, right? They both have values all along X from those 2 points, and they have values all along the Y's from those 2 points. But those are the extremes, and that's all there is to that problem. Yay! Fabulous. Okay, let's move on to lesson 36.5. This is another one of these problems that comes up often in standardized tests. It's not all that difficult, but it just requires a little bit of, I don't even want to say tricky thinking, but clever thinking that allows you to see what they're trying to get at. Okay. So in this one, we're talking about the area of a rectangle. So what I want to do before I draw the changes, we're just going to say, okay, if you multiply if you're trying to find the area of this rectangle, you just multiply length times width, and we're going to call that 1. We don't know what those numbers are, but we're just going to say it represents 1. Now we're going to change the rectangle. I'm going to make mine look the same. But John says that we're going to increase the length by 20%. So the new length is the old length plus 0.2 times the length. Let me scooch up a little so you can see better. And we're losing 20% on the width. So the width is minus 0.2 of the width. So what we want to do is run these numbers through and see what we get. Okay, and we'll compare it to that 1. If we add, this is like a 1L, right? So 1L plus 0.2L, that tells us we have 1.2L times, and here we should put the units here, 1 LW. And this is times 0.8 times the width, right? Here, I'll put these in parentheses so you can see it better. When we multiply, what I'll do is I know I can do 12 times 8 in my head. That's 96. But I see 2 decimal places, so that tells me the decimal goes right there. So when we multiply to get the area on our second rectangle, the one with the changes in it, we get 0.96. This one we got 1. So what that tells us is if we consider this 100% and we consider this 96%, the second triangle decreased by 4%. And that is the correct answer. The trick to this is knowing how to adjust these abstract measurements to take into account the changes. The first one will always be considered 100% or 1, however you want to think of it. John gave the answer. It asked us for a percentage decrease, so that's how I knew I should think of the 1 as 100%. And then this came out beautifully. It was easy to transfer that over, okay? So it was making these changes that was really the tricky part. That's a good problem. I don't really, I don't consider that too tricky, but it is hard for a lot of students to remember how to do that. So it shows up often on standardized tests. Buyer beware. All right, this last one is my least favorite of the problems that you guys asked me about because we have not, like we talked about again, we have not been taught enough about how to graph functions for this really to be a fair question. Reciprocal function 21. The equation of the function whose graph is shown is, and I'll write it down, f of x equals 1/2 x squared minus 2. Okay, and it shows a function, and I'll just sketch it in here. If we really need to look at it carefully, I'll draw it. It starts at I guess it's just minus 2. Yeah. Here, here, here. This is the way that it goes. Okay, sorry. Well, it's kind of wobbly. It's cute. This is minus 2. This is plus 2. This is minus 2. Okay, that's what we need to know. Make a sketch for the graph of the reciprocal function. So we'll call the reciprocal function the g of x, and we'll write that as 1 over 1/2, sorry, I wrote that wrong, 1/2 x squared minus 2. Well, this is a complex fraction, and we can't have that. So let's fix this. How would we do it? We would smush, and then we would flip, right? Thank you, Evie. In order to smush this, we have to have matching denominators. And so let's make this minus 4 over 2. So this will become x squared minus 4 over 2. And then that's just this simplified. So the reciprocal would be 2 over x squared minus 4, right? And we would multiply that once down here. This would cancel. I ran out of space. That's why I'm not writing it there. But then we would multiply it again up top. And so this is our new g of x, right? G of x equals. Okay. Let me just double check and make sure that's right. 3621. Yes. This is correct. Now, I consider this to be fair game. To ask you if this is the parent function, calculate the reciprocal function, right? And that's what we did. Remember that to find a reciprocal function, you take 1 over the old function, the parent function, if you will, right? That's different than an inverse function. With an inverse function, you take the original function, and it usually helps if you write it with a y. You solve for x. That's the first step. You solve for x. So in this case, what would we do? We would subtract the 3, and we would get x equals y minus 3. And then you switch the x and the y terms around. So we would rewrite it as y equals x minus 3. Okay, I expect you to know the difference between a reciprocal function and an inverse function. I expect you to know how to calculate them properly. I don't necessarily worry about the graphing part of this now because, like I said, we're going to get into graphing more later, but we haven't really been focusing on that, so I don't know how reasonable it is to throw this at you. But let me just show you what the answer looks like. What John is saying is that we're going to have asymptotes where the parent function crosses the x-axis, okay? And what that means is that we go out 1 more and up 1 more from where it crosses, and we put a point there. We go out 1 more and up 1 more, like so. And then our asymptotes will curve like so, all right? And this is similar to the ones we've done before. I'll draw a picture of that just to remind you, okay? So here's where our parabola is crossing the x-axis. So that helps drive the place where we're gonna place an asymptote. But an asymptote always goes to, it always goes 1 over and 1 up from there, because that's the place where the reciprocal function and the parent function are the same, because 1 over 1 is 1 over 1. That might be confusing. The weird part about this one is that the negative part of the asymptotes goes like this. It would be, again, it would be 1 and 1 out from here, right? 1 unit over, 1 unit down, 1 unit, and then from here, 1 over, 1 down. Okay, and instead of going on endlessly like this, right? If we drew these separately, they would go like this and like this, right? But because they intersect, we just take the part that they share. And so that would be the bottom asymptote on this parabola. Sorry, John, I think that's crazy. Okay, and let me show you. So this is, the purple is our parent function, and the green is the reciprocal function of the parabola. That's really hard, you guys. If you understand it at all, just, I'm glad. Remember that we've mostly been looking at lines, and if this is our f of x, right, and it goes right through, f of x equals x, that's what we've been doing, right, is the x and y. Remember that the way we calculate these is that we go over 1 and up 1, we put a dot there, it overlaps in these, and then we go down 1 and over, want to put another one, and then this is where our asymptotes fit. We draw the asymptotes 1 unit up and over, 1 unit down and over from where our line crosses the x-axis. Here we have 2 places. That's why we have 2 asymptotes, right? This would be like this and like this. Here we would have 1 there and 1 there, but these 2 intersect and make kind of like a weird shared one, all right? This is what we've done in the past, and we have also played around a little bit with these. Where we've shifted that, okay? Let me know if this helps. I can go through these graphs in a little more detail, but I don't want to bog you down too much in the details around that. It's much more important to me that you understand these differences. A lot of students confuse reciprocal with inverse, rightly so, their names are very close, right? But it's more important to me that you know how to calculate them and you know the difference between the 2. All right? The other thing I'll say is that with reciprocal functions, the interesting thing about them is the way their graphs interrelate. With inverse functions, the interesting thing about them is that you can basically work the same problem in opposite order. And that's how we use them in trig, right? We go basically backwards. We go in the opposite order using different information. So this is the good stuff. All right, those are the 4 problems. I hope that helps. I hope you have a great Turkey Day. When we do talk after the break for Thanksgiving, let me know if this helped, and I will do more to explain if necessary. Thanks, ladies.